Make sure I start recording. All right, so we're looking at, and we've done this in lab already. So right when the equilibrium lab, you saw the effects of this Chalteliers principle. So you're probably introduced to it there, right? If we think about the, I don't know which camera to look at here. If we think about the equilibrium being a stable sort of seesaw, we're going to add stresses to cause one side of this to come out of balance, and then we're going to observe the shift to go back to balance, right? So you'll see me a lot of times refer to this seesaw type arrangement based on the idea that we want at equilibrium, the amount of products is balanced with the amount of reactants, right? And that balance is defined as our equilibrium constant. And if we change that equilibrium constant, all we're really doing is shifting that fulcrum, if you will, about where that balance is achieved. Okay, so let's look at some examples in terms of our challenge problem. So if we look at a challenge problem where we have this reaction, CH or C2H4 as a gas plus Cl2 as a gas is in equilibrium with C2H4Cl2, right? And our job as chemists is to try to maximize the production of this, right? So we want to try to come up with ways to maximize the concentration of C2H4, or we want its concentration to go up, right? So we're trying to find ways to change this equilibrium to force things to go towards the products. And we have a list of 4 potential possibilities in which to do this. And we want to see which one will actually cause this intended outcome. Right? The first thing that we could do is we can change the volume. Right? We can go from a fairly small volume to a larger volume. And when we do that, that's going to affect, since it's a volume, it's really only going to affect those things that are in a gas, right? Because those are going to then expand to take up whatever space there is, right? So all of these are gases. So if we have more room, we're going to find that this molecule, this equilibrium, is going to shift in order to get more. So as the volume increases, we shift toward, not mole, more moles of gas. I don't know why I spelled gas with 2 S's, right? So if this case, in this case, we're adding the volume, we're going to shift towards the more moles of gas. In which direction does that shift occur then? Right? On this side of the reaction, we have essentially 2 moles of gas. On this side, we have 1 mole. So in this, when we increase the moles of gas here, we're going to cause a shift toward the reactants, which is going to cause this concentration to decrease. So this is not a good tactic to use, right? Because we would actually suppress the amount of the C2H4Cl2 that we wanted to produce, because the shift is going in that direction. Questions on that? Now, if we look at this one, if we can find some way to remove this C2H4 gas, now this concentration of C2H4Cl2, or pressure, I guess would be the better way to think of it. The partial pressure of C2H4Cl2 is going down, right? If it's going down, that means that we have fewer moles of that product than we should at equilibrium, which is going to cause our shift to go in that direction. It's going to shift toward the loss, right? So this would be a good tactic. Just see here. Right? As long as we are able to collect this stuff that we're removing. And because it's going to cause more of it to be formed, we're going to cause that equilibrium to shift towards that direction. What about lowering the temperature? Well, lowering the temperature is really going to affect K, right? But that may increase the amount of products, right? So this is going to change. Lowering the temperature will change our equilibrium constant K. We can predict how it's going to change. And with that prediction, we can actually, it's going to cause a shift, which means that we can either form more or less of this product, right? If we look at this in terms of where heat is, if we come up here, we say that this is an exothermic reaction. So heat is on which side of this reaction? If it's exothermic, which side would heat? Sorry, go ahead.
Is it the right?
Which would be the
Products.
Yep. So we can add the word heat here, right? So if we are reducing the amount of heat, right, that's going to make that side, that's going to cause the amount of heat to go down. So this is actually going to shift it again towards that reduction, right? Which would be towards the product, which means that K would actually, the value of K would actually be getting smaller when we reduce the heat, right? The actual K, but that would result in more products. So this would actually be a good tactic. Okay. And lastly, if we increase the amount of Cl2, right? So as the Cl2 increases, that's going to make more reactants than we should have. That is also going to shift. It's going to shift away from the addition. So this would also be a good tactic. So there's a variety of ways we can do this. And in fact, if you were in industry, you would probably choose the least expensive one, right? Or a combination of things. You would probably try to find a way to selectively siphon out the product that you're interested in. You would want to make sure that the temperature is at the lowest possible temperature where things are economical, right? So we wouldn't be adding temperature. We wouldn't necessarily be taking temperature away if that costs money. And we would be finding a way to continuously add, or we would have an excess amount of Cl2. All of those would be work in order to maximize the production. But all of this, we are looking at shifting an equilibrium from one direction or the other based on how it's going to impact this value of K. Questions, comments? All right. So let's stop the recording.